Now that we've presented our 2-transistor current source, we want to move on and look at our 3-transistor current source. And so a natural question to ask would be, why should we even bother with a 3-transistor current source if our 2-transistor current source was getting the job done? And so in answer to that, ideally we want our I out, our output current, to remain constant. Now of course we can't have that remain perfectly constant, but we would like it to remain as close to constant as possible. And so in general, there are going to be two things that are going to cause issues with our I naught being constant, at least that we're going to consider here, and those are going to be variations in our current gain beta, as well as variations in our VCE voltage for our output transistor, which we looked at with our video on the early effect. So we want to be able to improve our transistor current source in terms of stability with respect to variations in beta and stability with respect to variations in our collector emitter voltage on our output transistor. And so the first configuration that we're going to look at that can help us with this is our 3-transistor current source, which we can see here. So obviously, as the name implies, we've added this third transistor Q3 in the top. So before we talk about this, let's go ahead and label some currents and voltages to help us be able to talk about it a little easier. So over here, we're going to call this current through our R1 our I ref, the same as we did with our 2-transistor current source. And of course, we can label all of our base, collector, and emitter currents like normal. So for our Q3, we're going to have a base current coming in here, IB3. And we have here for our Q1, our collector current IC1. And coming back over here to our Q3, we notice that this is our emitter because it has the arrow on it, so this is our current IE3. And we notice that this current IE3 splits into two parts. One part is our base current for Q1, so we can call this IB1, and the other part is our base current for IB2. We also still have our voltage, VBE, because we don't have any resistors in this area here. From KVL, we saw that the base emitter voltages for Q1 and Q2 are the same. And then finally, what we want to label for our first discussion here is this IC2, which we are also calling our output current I out. And so as I have labeled here, this is just going to whatever output circuit we have. And so let me actually label one more voltage in here. We want to label our VBE3 for our Q3. So that's our base emitter voltage for our Q3. Okay, so a couple things to note before we get into the details with our KCL and our KVL and all of that. So we're still assuming that all of these transistors are matched. So let's just write that explicitly. So all transistors are identical or matched. And so what that means is that we have our base currents, IB1 and IB2, are equal to one another because we have the same base emitter voltage. So we have the same VBE for Q1 and Q2. So because of that, we have the same base currents, IB1 equals IB2. And what that means is, because again, they're identical transistors, they have the same beta, beta 1 and beta 2. And so that means we're going to have IC1 equals IC2. And so again, we can just write that this is because VBE1 equals VBE2, and up above we've just labeled that as VBE. Okay, so one other thing to note is, as we kind of talked about when we were labeling these currents, we can see that Q3 is supplying our IB1 and IB2. So Q3 supplies IB1 and IB2, and what we're going to see is that means that these base currents have less dependence on IREF. So less dependence of base currents on IREF. So as you recall in our 2-transistor current source, we are essentially pulling our two base currents directly from this IREF. But let's think about our basic transistor operation and see if we can't think through this. So remember that our base current is typically much smaller than either our collector or emitter current. And so what we see here is we have this emitter current is essentially equal to 2 times our base current. So the emitter current IE3 is relatively small compared to the emitter currents of Q1 and Q2. And even though that emitter current is on the order of the base currents for the other transistors, that means that our base current for Q3 is actually going to be much, much smaller than our base currents for the other 2 transistors, because we'd have to divide by roughly a factor of beta in order to get our IB3 value. Now, so what that means in terms of IREF is we can think of IREF as coming down here, and then it gets split into 2 parts, our IB3 over here and our IC1 right here. And so we're pulling off less of that IREF in order to get our IB3 that is ultimately creating IE3, which is feeding IB1 and IB2, as opposed to before where we were just pulling IB1 and IB2 directly off of that. So we're pulling less current from IREF. So that means as IREF is changing, we're not going to be affecting it as much by pulling off that IB3. So one thing to note though, as we're saying, we have smaller currents in Q3. So what that means is because we're operating at a lower current level, we're typically going to have a different beta value. So we know that our current in Q3 is lower. So that's what we were just talking about, lower than Q1 and Q2. So what that means is we're going to have a smaller current gain or smaller beta value for 3. And so that's just basically the operation principles or the physics under our BJTs. If you look at a data sheet, you'll see different values of beta based on current range. You'll know that as current gets smaller, for most transistors, the beta is going to get smaller as well. Okay, so what that means then is that we can say we have beta 1 equals beta 2 because we're saying those are matched transistors, and we'll just call that in general our beta. And then we'll say we have this beta 3, which even though these transistors are identical, because Q3 is operating at lower currents, we're going to say this beta 3 is less than beta. So again, that's for Q3. Okay, so now let's get a little more into the details of our KCL and all of that. So let's come up here and let's maybe just bring this circuit down here so I don't have to scroll up and down to see it. Okay. There we go. Okay, so we're going to start by doing a KCL in a few places. And so this is kind of going to seem arbitrary, but basically what we're going to do is we're going to set up some relations from equations, and ultimately we're going to kind of combine them together to get our expression for our output current in terms of our reference current. So if we do a KCL at this node here, and let me switch to highlighter colors so we can see this better. So if we do a KCL here, what we're going to see is we have IREF is equal to, and we kind of already talked about this, IC1 plus IB3. And we said, well, we know that because Q1 and Q2 are matched, we know IC1 is equal to IC2, so let's go ahead and change that to IC2, and we'll leave this as IB3. And so the reason we want to do that is, of course, we are setting this up to solve for IC2, which is our I out. And so let's call this equation 1 to be consistent with our notes. Okay, so we can also do a KCL at this node here. And so what that's going to look like, and again, we kind of talked about this qualitatively, is going to be our IE3 is equal to IB1 plus IB2. And again, because these are matched transistors, Q1 and Q2, like we had said previously, IB1 is equal to IB2. So let's just say this is equal to 2IB2. And again, I'm putting this in terms of IB2 because ultimately we're going to want it in terms of IC2. Okay, we also know that we can relate IB2 and IC2 if we're operating in forward active mode, which I've implicitly assumed we are. So we can say IB is equal to IC divided by beta. And so let's call this our equation 2. Okay, so now what we want to do is take a step back and consider our transistor properties. So we have certain equations that are always true for our transistor, regardless of what mode it is operating in. And so that is that our emitter current is equal to our base current plus our collector current. So we're going to look at that for our transistor Q3, which is the new one that we've added sort of a little higher up. So we can say IE3 is equal to IB3 plus IC3. Okay, well again, I can relate our IB and our IC with our current gain beta. So I'm going to say this is IB3 times 1 plus beta 3. And so notice here I'm specifying this beta 3 as being unique from our beta for Q1 and Q2. So we can rearrange for this a little bit to solve for our beta 3, or sorry, not for our beta 3, our IB3. So we can say our IB3 is then equal to IE3 divided by 1 plus beta 3. And so let's call this equation 3. Okay, so now we sort of have all the pieces. We just need to put this together. And so essentially what we're going to do is we're going to take our IB3 from equation 3 and we're going to put it into this equation 1 here. So let's go ahead and do that. And so this is written explicitly in the notes, but I'm not going to bother writing that. We're just going to take this IB3 expression from 3 and substitute it into 1. So if we do that, what we get is our IREF, change back to black here real quick, we get that our IREF is equal to IC2, and now we're subbing in for our IB3 expression, which is IE3 divided by the quantity of 1 plus beta 3. Okay, and so we can call this equation 4. And so now what we're going to do is we come up here and we say, well, we already had an expression for our IE3, so that was in our equation 2, right? So here we're going to take this expression for IE3 from 2, and we're going to substitute this into equation 4 for IE3. Okay, so let's do that. So now we have IREF is equal to IC2, still just hanging out up front there, plus, now I'm going to bring this 1 over 1 plus beta 3 sort of out here to be by itself for a second, and that's being multiplied by, we substitute our 2IC2 over beta. And so now we can just rearrange this. So we can say this is equal to IC2 times 1 plus 2 divided by beta over 1 plus beta 3. And now, of course, we can solve for our IC2 in terms of our other variables. And the reason we're interested in that is, of course, that is our I out. That's our output current. And we see that this is going to be equal to, we're going to have IREF in our numerator. And then in our denominator, we're going to have our 1 plus 2 divided by beta times 1 plus beta 3. So that would be our expression relating our output current IC2 to our quote-unquote input current IREF. So it may not be immediately evident when we look at this equation, but what this actually provides is that compared to our 2 transistor source, our I out is going to be closer to IREF. So let's just make a couple comparisons here real quick. So compared to our 2 transistor source, we have that I out is closer to IREF. And so the reason that is true is if we look a little closer at this, we can see that this 2 over beta times 1 plus beta 3 is actually going to be a lot smaller than the factor we had in the similar equation for our 2 transistor current source, which was just 2 over beta. So even though our beta 3 is smaller than our other betas, we notice here we essentially have a beta squared. We have beta times beta. So of course that's going to be a lot larger than beta, which means that overall value is going to be smaller, which means this 1 is going to dominate and our I out is going to be closer to IREF. Okay, so another difference that is not obvious from this equation but we could talk about is that there is less variation in our output current with respect to beta. So less variation of I out with respect to WRT with respect to changes in beta. And so a good example of that is actually on page 694 in the Neiman textbook. And so there's an example where they use PSpice, and you can look through that. But basically the main result I'll sort of sketch here is a table where we have our output current and our beta. And so basically what they're doing in PSpice is they're able to sweep this beta value through different values and see how that affects our output current. And so if you do the simulation for a 2-transistor current source, you get something that looks like this. So a relatively large range of variation. So this is our 2-transistor source. Now if you were to do the same thing with our, let me get a slightly different color, with our 3-transistor current source, it ends up looking closer to this. So we see a lot less variation. So this would be for our 3-transistor source. So I'd encourage you to look through that and maybe even try that out in PSpice yourself, because being able to sweep variables is a useful thing to do, but we unfortunately just don't have enough time to get into all the details of everything. Okay, so one other thing that is useful to do is to be able to find what this Iref current is based on our voltages that are biasing the circuit. So let's once again copy the circuit down here, and we can take a closer look at that. Okay, so here's our circuit. And so what we're going to do is we're going to do a KVL to figure out what our Iref is. And so this is going to be very similar to what we did for our 2-transistor current source. We're going to say we essentially start down here at this potential of V minus. We're going to go through our VBE. We're going to come up this way through our VBE3. We're going to go through this voltage through our R1. And then at the end, we're going to be at this voltage V+. Like I've mentioned in previous classes, if it makes you feel better to draw explicit loops, of course we could draw in, for instance, a voltage source here. That is a value of V minus, and then we could connect this over here to our voltage source, which is going to be V+. So again, if that makes you feel more comfortable, by all means, feel free to do that. But as our circuits get more complicated, that might not be feasible. Okay, so doing that KVL, we have V plus is equal to, so we said we start at V minus, we go through a rise of VBE, so plus VBE, we go through our rise of VBE3, and then we go through that rise across the resistor, which is going to be Iref times R1. So for a first approximation, we can say that our VBE3 is about VBE. So let's just say first approximation. And so you notice we'll be doing this a lot through this class. We can say, to a good approximation, we can simplify this. It's going to make our answer a little less accurate, but it's going to save us a lot of work in terms of the math. Of course, if we want a more accurate answer, we can decide when that trade-off is worth more work. And we can also go through and use some simulation software such as PSpice if we want to get something much more accurate. But at any rate, if we use that approximation, we now have 2 VBE, and we arrange this to solve for our Iref, and we get an expression that looks like this. So this is how we could solve for our Iref in terms of our bias voltages and the resistor. So the last thing that we want to talk about in terms of this 3-transistor current source for now is our output resistance. And so of course this is related to the discussion we had about our early effect and our output resistance for our 2-transistor current source. So our output resistance is actually going to be unchanged compared to our 2-transistor current source. And that's because we're still just looking into that collector of our Q2. So unchanged compared to our 2-trans source. And like we said, we're still looking into collector of Q2. So I'll scroll up here and we'll see exactly what I mean by that in a second. So collector of Q2. So let's come look at our circuit, and basically all that's saying is for our output, we're looking into this collector of Q2. So we're going to get our output resistance from that the same way we did with our 2 transistor source. And so as you recall, for our early effect lecture video, we found that the change in our I0 with change in VCE2 was equal to I0 over VA, which is just equal to 1 over R02, where R02 is a small signal output resistance looking into the collector of Q2. So the reason this is important is this is saying that we have no improvement in terms of variations of output current with changes in that collector emitter voltage. So no improvement for variations of I out as VCE2 changes. So essentially what we see is this 3 transistor current source. We've added a little more complexity, we've added more components, and namely a 3rd transistor Q3. The advantage is we've made it less sensitive to changes in beta. However, we've not made any improvement in terms of changes, how our I0 is stable with respect to changes in VCE2. So of course what we're going to look at in some later configurations is how we can approach both of these problems.